Hi, thank you all so much for watching the second part of this talk about how Khovanov homology detects the torus link T26. In this talk, we'll go over the details of the proof that Khovanov homology detects this torus link T26. This talk is self-contained, so you don't need to have watched the first half of this video to follow the talk. However, the first half of the talk gave much more context about Khovanov homology and link detection more generally, so it provides a lot of motivation for why one might want to know that Khovanov homology detects the torus link T26. So with that being said, we can get started. So before I talk about any math, I just want to take the time to acknowledge that I'm recording these videos on the stolen territory of the Massachusetts people. I think it's just important to take the time to say this as part of reflecting on the history in the United States of a continuing colonialism and genocide from the founding of the United States through to today. So with that being said, so I'll be talking about Khovanov homology detecting the torus link T26. So as a very brief overview, remember Khovanov homology is some invariant of a link in S3 that was defined by Khovanov. And given a link, it's some bigraded abelian group where it's graded by quantum grading J and a homological grading I. So in this talk, we'll give more details about how to prove this theorem that I showed, that if Khovanov homology of your link L is isomorphic to the Khovanov homology of the torus link T26, then L is actually isotopic to T26. So another way of saying this is that Khovanov homology detects the link T26. So we'll cover like all the framework we need to prove this detection result. And as a warm-up, we'll use this framework to prove that Khovanov homology detects the hop link. And we'll do this in some detail. And every step of this is then mirrored in the proof that Khovanov homology detects T26. And so at the end, we'll then see, well, how could we repeat this process with T26? And so I should say that the fact that Khovanov homology detects the hop link was originally proved by Baldwin, Sivak, and G, and they used a different proof than what I will show here. But the proof I show here is to generalize to the fact that Khovanov homology detects T26. So how do we prove that Khovanov homology detects the hop link? So say we had some link L that has the same Khovanov homology as the hop link. What we could first do is show that L has two components and that the linking number between these two components is 1. But we might ask, what sort of link could L be then? So this is an example of some link that isn't the hop link that has two components and the linking number between these components is 1. So we would want to rule out a link like this. So we could then show that each of our components was actually an unknot. So that would rule out the link we saw before, where one of our two components was a trefoil. But there's still a link like this, where we have two components. The linking number between the components is still 1, but and both the components are unknots, but this still isn't the hop link. So we want to rule out a link like this as well. So finally, you could show that one of the components is a braid in the complement of the other, which would rule out the link that we saw before and other links like that. And so this is actually then the only knot link you could show with two unknotted components where their linking number is 1 and one of the components is a braid in the complement of the other. So you've shown then that Khovanov homology detects the hop link because this is the only possibility. And so our link L is the hop link. So now what we can do is we can talk in more detail how do we show each of these steps, knowing that L and the hop link have the same Khovanov homology? So for the first step, we would want to use a spectral sequence from Khovanov homology to Lie homology. So Lie homology always has rank 2 to the number of components. And what's Lie homology's generators come in pairs of 2 that sit in the same homological grading. And if you have a 2-component link, the difference in homological gradings between your 2 components records the linking number of the components, specifically twice the linking number of the components. So looking at the Khovanov homology of the hop link, if we had a link whose Khovanov homology looks like this, well, because we have a spectral sequence to Lie homology, we see that Lie homology would have to have rank 4, and it's supported in homological gradings 0 and 2. So this difference between these homological gradings is twice the linking number, so the linking number is 1. And so we have a link with 2 components, and the linking number is 1. So that's our first step of our proof. So now what we want to do is show that each of those 2 components of our link is actually an unknot. And so to show that, we would want to use the link splitting spectral sequence defined by Batson and Seed. So this is a spectral sequence from the Khovanov homology of a link to the Khovanov homology of the disjoint union of its components, which is also the tensor product of the Khovanov homologies of its components. So then what we need to do is we could recall that for any knot, the rank of its Khovanov homology is at least 2. And Kronheim and Mrfka have shown that if the rank of Khovanov homology is 2, then your knot is actually the unknot. So taking this link splitting spectral sequence and looking at our example with the hop link, so we know that our link L has the same Khovanov homology as the hop link. Well, then its total rank of its Khovanov homology is rank 4. And so using this link splitting spectral sequence, we see that the Khovanov homology of the split link built from the 2 components of L has rank no greater than 4. And so the rank of the tensor product of the Khovanov homologies of the 2 components is no greater than 4. And so that tells us that the rank of each component's Khovanov homology is no greater than 2. So that tells us that both of our components are actually unknots. So now we've seen that we have 2 components. We know their linking number. We know that they're both unknots. So our final step for detecting the hop link is showing that one of those unknots is a braid in the complement of the other. To do this, we need to use some Floor theoretic data. So we'd want to use knot Floor homology that's been introduced by Ajwa Sabo and independently Jacob Rasmussen. And it's a categorification of the Alexander polynomial, and it's also bigraded in some way by a Maslov grading and an Alexander grading. And link Floor homology is some generalization of this that carries an Alexander grading for each component of your link L. And collapsing all those Alexander gradings recovers the knot Floor homology of your link. So to relate the Khovanov homology of our link to this, what we need is the Dallin spectral sequence constructed by Nate Dallin. That's a spectral sequence from point in Khovanov homology to the knot Floor homology of a link. And what we get from this spectral sequence is a rank inequality telling us an upper bound on the rank of the knot Floor homology of our link. And so before we do that, we would just want some properties of a knot Floor homology. So one is that for link Floor homology, it's symmetric about some Alexander gradings. And there's also spectral sequences from link floor homology to the link floor homology of a link minus a component tensored with some two-dimensional vector space V. So this is important as a way to help us build what the link floor homology of our link looks like in some way. And finally, we need to know that link floor homology detects braids, because that's what we're ultimately trying to show, is that for our example, one of the unknots is a braid in the complement of the other. So it's good that link floor homology detects braids. And specifically, for a two-component link, if the dimension in the top Alexander grading associated to an unknotted component is 2, then the other component is a braid in the complement of that unknot. And so one way to see why this is true is by basically the same sorts of techniques that show that knot floor homology detects fiberedness by having your highest Alexander grading have rank 1. If you cut open along the Seifert surface associated to your unknot, you'll roughly speaking get a product sutured manifold if and only if the other component of your link is a braid in the complement of that unknot. So now we can use these facts to prove that Khovanov homology detects the Hopf link by showing that if we have the same Khovanov homology as the Hopf link, one of our unknots is a braid with respect to the other. So from the Dallin spectral sequence, we get that the rank of link floor homology of our link is no greater than 4. And then from the fact that we have these spectral sequences to the knot floor homologies of either component of our link, and additionally, the symmetry that we know link floor homology has to have, you can actually deduce that this is what the link floor homology of L looks like in Alexander gradings associated to the two components of your link. So it's rank 4 and it's supported in these 4 Alexander bigradings. And so then now if we look at, say, the Alexander gradient associated to our first component, we see that in the top Alexander gradient of 1/2, this link floor homology has rank 2. So that means that the other component is a braid in the complement of this unknot. And so that means that we've shown that our link L is actually the Hopf link. So now what we can talk about now is how to generalize this sort of approach to showing that Khovanov homology detects the torus link T26 instead of the Hopf link, which is the torus link T22. And so really we take the same approach, but some of the steps require more work or checking more cases. So if we assume again that we have a link whose Khovanov homology is the same as T26, our first step is we could use the spectral sequence to Lie homology to again see that L has 2 components and that the linking number between these components is 3. And here, this is basically the exact same as in the case of the Hopf link. There's not much more work to be done here. And so again, here's an example of a link that satisfies those conditions that isn't T26. So when we're ruling this out, we'd then use the link splitting spectral sequence to see both components are unknots. And here you do need to do a little bit of casework to rule out the case where one of the components is an unknot and the other is a trefoil, which you didn't have to do with the Hopf link. But it isn't too hard to do, it's just a little bit of extra work. So now here's an example of a link with 2 unknotted components, and the linking number is 3. That's not T26. So to rule this out, just like in the case of the hop link, we'll now want to use the Dallin spectral sequence to show that one of the components is an unknot. One of the unknotted components is a braid in the complement of the other unknot. And so here there's just a lot more casework to do in terms of what can the link floor homology of this link look like from knowing some basic facts about it and knowing some upper bound on its rank. And so this is the same idea as the hop link proof, but just a lot more work than what was shown here in terms of narrowing down to the fact that one of the components is a braid in the complement of the other. So now that you've done this though, these are the only 3 links who have two unknotted components and their linking number is 3, and one of the components is a braid in the complement of the other. Because these are the only 3 braids up to conjugation whose closures are unknots. And so finally from here, all you have to do is check in this list that the Khovanov homology of the other links is different from the Khovanov homology of T26. So once you've checked that, you've then proven that if the Khovanov homology of L is isomorphic to the Khovanov homology of T26, then your link L is T26 because you've showed that it was in this finite list, but everything in the finite list besides T26, you can check has a different Khovanov homology. So Khovanov homology detects the link T26. So thank you all so much for your time and for watching this video. If you have any questions, please leave them in the comments so I can try and answer your questions. But thank you again. I hope you all have a great day.